Hello everyone, welcome back. Continuing on with heat flow and rifting and extensional tectonics. The oceans. The ocean lithosphere is our extreme case of how extension and what's really rifting affects everything we see about the seafloor all through these thermal processes. And the reason for this is because the lithosphere is young and it's formed from molten mantle. So if we go to a mid-ocean ridge, the rock that we find there is coming straight up out of the mantle. In fact, the temperature of the asthenosphere is in fact risen up right to the surface, which is why we have so much volcanism right at the surface. And we're forming this new lithosphere at this point. It then moves away from the ridge, and as it moves, it cools. And in fact, the lithosphere is being formed through this thermal cooling process. Well, as we were just talking about moments ago, that cooling process is described as a diffusion process through this differential equation here on the left, which is the diffusion equation. Again, kappa is the thermal diffusivity now. So this is the time-dependent temperature that's going to describe the temperature in the oceanic lithosphere. What does that look like? Well, to do that, we have to think a little bit about the time-space relationship. So if we think of a column of lithosphere at one time and we track that through time, it's going to move, right? It's going to move away from the ridge. This is this basic principle of space-time interchange here along a distance from a ridge. But the temperature, the reason why this gets longer and the lithosphere gets thicker is because the temperature is going down. And to predict that, we can then look at the solution to this equation with the proper boundary conditions. The proper boundary conditions and initial condition are that the entire lithospheric column at the ridge has a temperature of the asthenosphere. We can call that TA, for example. That's the temperature of the asthenosphere. The base of the lithosphere also has that temperature. So what we have is we have a boundary condition where the temperature is equal to the surface that's not correct. It's equal to the surface temperature, T, which should be a T0 or something, at x equals, oh, sorry, no, that is correct. I'm sorry, this is the initial condition. It's TA at x equals 0, and it's T equals 0 at z equals 0. So at the upper surface, it's 0, and at a depth deep in the lithosphere or the asthenosphere, then it goes back to TA again. So if we take that initial condition and this boundary condition, we can then solve this equation. Again, you can integrate it twice, but you get a rather complicated solution here now that's written out like this, where T is equal to TA times ERF. ERF is the error function, and that's defined as an integral function. This is just a simple analytical function like a cosine or a sine or an exponential. It just has a definition that's in terms of this integral quantity. And this is simply integrating the e to the minus anything, nu to the squared, because it's a definite integral. This nu disappears and you get a number. So for any given number nu, you'll get a value of the ERF function like this. If you want to see something more about that, you can go to Wikipedia or anywhere you'd like and look up what exactly this looks like. For values from 0 to 2, 2.5, the error function will take on a value from 0 to 1. That's it. That's its full range, 0 to 1. There's a second function, which is called the complementary error function. That also can be quite useful in writing these things down. That's just equal to 1 minus the error function. In any case, this then is what's describing the temperature in the lithosphere at any depth and as a function of time. Right? So this is T, and the kappa again is the diffusivity in here. So the temperature is described by this function. The heat flow that's coming out of the top of the lithosphere is in fact described as the derivative of temperature with respect to depth at the surface times the thermal conductivity, which is this expression. Q is minus K times the gradient. That's the definition of heat flow from Fourier's law. So if we take this function and take the derivative once, we get a function like that, which is actually much nicer and simpler. This is just a square root of time function. So what this is saying is that the heat flow should be decreasing as 1 over the square root of time times a bunch of constants, right? Which is nice and simple. And that's something that's quite easy to test, because we can go out then into the real world, and if we can measure the flow of heat out of the ocean floor, then that in fact should be decreasing as we move away from a ridge. And that's exactly what these data are showing now. For two oceans, Pacific and the Indian, this is the heat flow at the base of the ocean in the sediments that are sitting under the ocean as a function of the age of that lithospheric plate. Right? And so our prediction from that cooling lithosphere model that I just showed you is that this should be a 1 over square root of age, which is this function here. And these then are the measurements. So what do you think? Do those fit or do they not fit? Well, if you can look, show you just another example. Here's for different spreading rates, but again, this is the same sort of data, heat flow versus age of the lithosphere. And in fact, they don't fit terribly well. The theoretical profile, again, is 1 over square root of age, but the observed profile is something kind of complicated and messy, but it's definitely always less than the predicted heat flow that we expect to get out of the lithosphere. Why is that? Does this mean our theory is wrong? Normally that's what we say, right? If the theory and the data don't match, the theory must be wrong because the data are the data. Well, here's a little hint as to what's going on. Here's a detailed heat flow profile across part of the ocean floor. What you're looking at the bottom figure here is seismic reflection data. These seismic reflection data show all these flat line sediments. That's what this stuff is. I know it's a little bit fuzzy, hard to see, but these are flat line sediments, and these lines that are interpreted here are the base of those sediments, or the oceanic crust sediment boundary. And this is the heat flow measured across this profile. And what you can see here is that the heat flow is extremely high over a small seamount here. It gets low where the sediment thickness is low, and then it goes back up where there's a seamount that here doesn't quite make it up to the surface, but it's very close. And again, the heat flow gets very high. So why is it that the heat flow would be low over the sediments and high over the bedrock, that is the oceanic crust, where it's either at or near the surface? Well, the answer to this, and this is actually the explanation for the heat flow data from the ocean floor, is this. And maybe you've seen pictures of this. These are black smokers. These are underwater hydrothermal springs or vents that are gushing hot water out of the deep crust. And these represent then water that's circulating through the crust. Here's another picture that's going down somewhere over the crust. It's getting heated, and then it's coming back up to the surface. And when it comes, it carries a lot of heat with it. That's a lot of hot water that's pouring out of these vents. When we're measuring the conductive heat loss out of the ocean floor, in fact, that heat loss does not include this hot water. So in fact, let me go back to this other figure. Say here, for example, these data are all lower than the theoretical profile because a lot of the heat has been removed by these hot fluids. And these are actually very common under the ocean floor, that these are anywhere where you can get water into the crust, it's going to be carrying a lot of the heat out, and that's going to systematically lower all of these data. So our belief now is that in fact the theory does match the data, or at least the theory is correct. It doesn't match the data because the data have a second type of cooling, one associated with that hot water. So in fact, we think our model is pretty good, and this prediction of the temperature, this is again the instantaneous cooling analytical solution for the temperature as a function of depth and time. Here is here's depth, here's time. So this prediction, and these are isotherms now that would be calculated from this this particular function right here, and we think that in fact the thickness of the lithosphere and the temperature within the lithosphere is predicted pretty well by this kind of a model. All right, why else do we think maybe this is correct? Well, the other reason we think this is correct is because the oceans get deeper, right? Older the ocean, the deeper the water. Why is that? Well, this is an isostatic argument. As the temperature is cooling, the rock, sorry, as the lithosphere is cooling, the temperature is going down, the rock is going to get heavier. And that comes from a relationship that we refer to then as the thermal expansion of the rock, which says that the density is going to be a function of some change of temperature through some kind of a thermal expansion coefficient. And this is a physical property of the rocks, looks something like this. But this temperature effect on density means that as the lithosphere gets cooler, it gets heavier. When it gets heavier, it starts to sink down deeper. And that then gives us the second prediction. Here at the top, again, here's the age of the floor against the heat flow, but here's the depth of the ocean floor against the age of the ocean floor. And this one does fit really nicely. So if we go through that temperature, same temperature solution, calculate the density, we can do a little isostatic calculation and calculate what the height of the ocean floor should be above some datum. We'll get a prediction of the depth of the ocean floor. You can plot it either way, depth or height, right? So here's the prediction of the depth of the ocean floor as the colored lines, and here are the observations. So here where the heat flow data did not fit very well, this fits really nicely. And this really gives us a kind of a support for this idea that it is this cooling of the entire lithospheric plate that's important for that subsidence that we're seeing here from left to right with the age. All right, so let's go start to take this to the tectonics part now. So at the moment, 70% of the Earth's surface is oceanic lithosphere. In addition to the oceans, which are all forming then from this kind of a spreading process, we also have quite a few large basins on cratonic areas that seem to be also associated with extensional tectonics. One of the arguments for this kind of a continental rift basin is that some rifts fail. For some reason, there's something, they get started, and rather than turn into an ocean basin, they simply stop or they fail for some reason of temperature, rheology, something like that. So we can start to look at these different types of basins and from a full ocean basin, say up to some kind of a continental rift, and try to sort of classify them, talk about their characteristics and so on. One of the ways that we look at that is what's called the stretching factor, which is this beta that's down below. This is just a strain measure that's saying that if we have some length, this is an L naught across, say, a rift like this, or an initial length, and we have a final length, which is L1, this beta is simply calculated by the ratio between the final length and the initial length. So that gives us a way of sort of defining then how much extension there's been across a system. An ocean ridge might be actually a beta approaching infinity, right? If we go, you're starting from essentially zero width and going to a full ocean basin, that's kind of an infinite amount of extension. So this is really more useful for things like continental rifts where we have a finite amount of extension. But if we think about this, then we can start to look at some of the different types of extensional basins that we have in the world and try to classify them in terms of their stretching factor. This is the beta factor for this, and maybe some other factors like what the strain rate, how fast are you doing the stretching and so on. But the first order is really to just talk about how much stretching has there been. So 1 means there's been no stretching. Infinity means we go to an oceanic basin. So for a factor of 1.2 or something like this, 1.5, somewhere in here, we get a little bit of extension. That extension in a continent in particular leads to isostatic subsidence. The crust is thinner, it's going to sink down. This is a kind of sag or some kind of a sedimentary basin. This can happen also inland from a continental rift where you get a little bit of stretching, and then for some reason instead of breaking here, it broke over here and started stretching here. Continental rifts usually have a little bit more, maybe a 1.5 to 2 stretching factor. And where we get really up to 2, then we're starting to get things that look like rifts. So things like a failed rift, I'll give you an example in the North Sea in a little bit, or big detachment systems that are stretching the crust or the lithosphere by a factor of 2. Remember, beta of 2 means we've like doubled the length, so that means you have to half the total thickness of the crust, depending on how it's distributed. But these big extensional systems might be a factor of 2 or so. And then we get up to the passive margins, which is the stretched continental crust just before breakup, or the final early breakup stage of the system. At this point, the beta is reaching something like 4. This is what we have then just prior to the formation of the ocean floor. So that once the ocean is being formed, these passive margins are preserved on the edges of the continents. So looking at a couple of these things, this is a cratonic basin. There's an example of a cratonic basin. So extension means crustal thinning. Crustal thinning means isostatic subsidence. This is an example from the Siberian basin, where we can see the crust sediment boundary here is several kilometers. This is going down 2 or 3 kilometers below the below sea level, and it's then filled with sediments. Right, so this is an example of a sedimentary basin. Here's another cross section across the same basin. It's deepest in the middle. It's shallower on both sides. So somehow this extension's been distributed across the basin. And you know, if we could see closer at the bottom, we might see things like normal faults. They're kind of marked in here. You can see some normal faults. Those are what are responsible for the extension of the upper crust. But what we really see is we see these sediments. We see the sedimentary basin that's filling the hole that came from the response of this isostatic subsidence. With a little more extension, you get things like this. This is a failed rift system. This is the Viking Graben, or the North Sea. So it's kind of a crummy picture, but this is up between Norway and Scotland. This is part of the North Atlantic spreading center, but it didn't turn into a real ocean. So the real ocean spreading jumped over to what's now the Atlantic Ocean, but this was stretching at about the same time. And you can see that, in fact, the crust has been thinned quite a bit. We have a big Graben system here. Here now, where we have a nice structural cross section, you see all these little normal faults. Lots of them. They're distributed through the upper crust. It could be that the lower crust is deformed ductily. It's the rheology, something that Whitney will talk about more next week. But you can see that there's a lot of thinning here. And again, we have sediments that are deposited over the top of the entire system. Examples of what we call a proto-oceanic trough. This is now really essentially a spreading system, a system that's gotten to the point of forming new oceanic crust, even though we don't have maybe what we call an entire ocean basin. Example of that would be the Red Sea, where the Arabian plate, it's a little small plate anyway, but it's clearly broken off from Africa along this rift system that is the entire Red Sea. It actually connects up down here to the East African rift and the Gulf of Aden. But this entire system then is is some type of a early stage ocean, if you'd like. If it continues, then it will eventually form another ocean here, right? There are certain characteristics associated with these kinds of system. In this case, for example, there are a lot of evaporites deposited between, in this case, 14 and 10 million years ago. Why is this important? Well, if there are evaporites, that means it was not below sea level. So the elevation of sediment, or in this case, salt was being deposited, was very close to sea level probably to form that. Usually for evaporites, you need to get salt water into a basin, evaporate the water, leave the salt behind. So it must have been right at sea level. Today they're underwater. So that means that there's been continued subsidence since that time. There are other characteristic sediments. First, there are following the evaporites are also then, for example, black shales or pelagic carbonates. These are all indications that we had a closed basin. It was not freely circulating water, but rather a closed, even a continental system for depositing that. We then start to shift into more marine sediments as we go up, and in particular, then there's what we refer to as the syn rift sediments, which in this case are shown as these sediments here. What defines syn rift sediments then? In this case, these are clastics, but you notice how here we're going across, this is this section here. Here we go across this section of the margin, bunch of normal faults here. These, either the black or more importantly, this stippled pattern in here, these have their thickness associated with the normal faults, meaning they're thicker here and they drape on top of the normal faults. This means that they're syntectonic. So they're being deposited at the same time that these normal faults were active, right? And that's, so this is what we refer to really then as these syn rift clastics or syn rift sediments. And in fact, there was a beautiful example back here of the same thing in the Viking Graben. Here, if you were to say, all right, what's the age of all the sediments you can see in there? The blue look like they're cut off by the faults, right? So all these blue sediments are chopped by the fault. Those are pre-rift sediments. And then the brown in here, there's no brown up on this side of the fault, is there? What does that mean? If you have sediments here and no sediments here, that means these were deposited up against that fault. That means these are syn rift sediments. And then after that, there is this stippled gray layer that goes across here and across here again, right? This is now draping over everything. It's covering all of the faults and the other earlier sediments. This is what we'd refer to then as the post-rift sediments. So if they're not deformed, this is just a cartoon, it's maybe hard to say, but if they're not deformed by the normal faults, then they're post-rift. So we have a kind of a pre-rift, a syn rift, and post-rift sequence of sediments that are deposited over this system. All right, well, passive margins. So what happens next? If we keep stretching, then eventually we're going to form an ocean. When we form an ocean, each side of that ocean basin becomes what we refer to then as a passive margin. These are the continental margins. They're not tectonically active. Once the extension is localized to the mid-ocean ridge, all of this extension, all these normal faults shut off. And that's in fact why we get this post-rift sediment. In this case, this big passive margin sediment wedge is labeled, that's deposited over the normal faults, the extensional structures, and the edge of the oceanic basin here. All the extension is now localized to this one point. All right, so at this point, extension stops, it starts to cool, the heat flow starts to go down again, they're seismically inactive. It's what we refer to as conjugated, in the sense that there's one side here and one side here, and in fact, you should be able to match those up, right? So you do your plate reconstruction, you know where are these things connected, and that defines this conjugated margin. We have the fault-bounded syn rift strata then, and then as you go oceanward, it starts to thicken and then eventually shallow out again into the marine sediment. But this is a good place to deposit sediments, because you've got a big hole, big ocean basin here. You're right next to the continent that's feeding sediments, so you tend to accumulate a lot of sediments on these passive margins. So passive margins around the world are very important, both as as sediment archives. They're telling us a lot about both the rifting and the post-rift process. There's a lot of volcanic activity here during rift or prior to rifting. In fact, they're often classified in terms of volcanic margins versus non-volcanic margins, which is what's being mapped here. But these are all the major passive margins of the world. There's also this question of how much fill is there. You can depends a lot on whether you have big rivers or what kind of a climate you had on land, whether or not you have what's say a sediment starved margin versus a sediment rich or sediment nourished margin. So these are conjugates where one side, in this case, this is the American side of this conjugate rift. It matches up with Iberia and North Africa along here, and on this side, like the Biscay margin, was very little sediment, so you see a big difference in the amount of sediment, say here versus here. So models of rifting. So first of all, let's look a little bit more detail at this rifting that I started to show you with the mid-ocean ridge, but now we want to look at this in terms of what do we see in the continental record. So again, these are these two major phases. A lot of this is based on the sediments, but it's also the deformation. We have a first syn rift phase, and then we have this post-rift phase. The syn rift being defined by the fault-controlled subsidence, post-rift being the overlying strata that are just kind of blanketing everything. So why is it that we see these, and what is it that then controls the subsidence? That's one of the things that we'd like to know. So I'm going to show you just a simple model, and you're going to have a homework that works with this as well. So here's a simple model for how we kind of think this system works and how we go about predicting then this syn rift post rift sediment. This is going to be a simple model of extension for the crust in the lithosphere. It's often referred to as the Mackenzie model because it goes back to a paper back in the 70s by Dan Mackenzie. So what do we want to do? What we're going to do here is we're going to look at two processes. We're going to look at the instantaneous stretching and subsiding, and then we're going to follow that by a gradual thermal subsidence, a thermal cooling and subsidence that goes along with that. So you can think of this as a variation on mid-ocean ridge cooling, if you'd like. If we make a set of assumptions about the thermal conditions and so on, we can come up with a relatively simple model that looks something like this. So here's our beta factor again. So we're going to talk about beta again. This is, again, the degree of stretching. is given by beta. So if we have an initial length of L naught and we're going to stretch that out to L1, that's going to give us then our beta factor. That if that stretching is balancing the mass so that the crust has to thin in the same area, then we're going to thin the crust by, again, the same factor of beta. So we have an initial crustal thickness and it's thinned to a value of this YC divided by beta. All right, so what happens if we do that? If we stretch this, we'll have an isostatic response, right? Immediately to this thinning, it's going to subside and we're going to get sediments that are deposited in here. Right, so here's the here's our kind of model. Okay, we have a before and an after. We can think about this again isostatically. We're going to think about two processes here, isostasy and temperature. So what do they look like? Well, here's the first thing is the temperature. Here's this purple line is a geotherm. That's the temperature with depth function for our initial condition here. Now what happens when we stretch the lithosphere and thin it? This point here, the base of the lithosphere is going to move up to this point here, right? And if it moves very fast, it carries its temperature with it. So the temperature doesn't change. So here we have the same temperatures down here in the purple. It's maybe a little hard to see, but this is the same temperature, but it's now distributed over a much shorter thickness. The lithosphere is much shorter. So we plot it over here together. This temperature here goes to here, and we have this as the temperature in the new stretched lithosphere. So again, if this is instantaneous, then the temperature is just carried up like this. What happens subsequently? Well, that temperature, that red temperature line, is not in equilibrium. If the lithosphere-asthenosphere boundary is still down here at 120 kilometers, it's going to cool. It's going to try to go back to that initial condition, and that means that the red line is going to try to go back to the purple line. And it does that by diffusion. So that with time, that heat that's here is going to diffuse out the top, and the entire lithosphere is going to cool off until it goes back to the purple line. So this is sort of like the mid-ocean ridge problem, except it's a little bit different in that our initial condition is not one temperature. It's rather this linear temperature distribution of this red line. But again, it's a diffusion problem, and again, it's a cooling problem. And cooling leads to subsidence. So really we have here then two parts. Now here I'm just going to throw this up on the screen, and in your slides you can have a look at this, but this then is the solution to exactly that problem, that stretching and subsequent cooling. And again, we can calculate the density from the temperature. If we know the density, we can go through isostasy and get a subsidence curve from that. That is a height for what that is. So, but just maybe we just look at this one again for a moment and think about this. So what is going to be the isostatic response just intuitively? Well, when we go from the purple to the green, if we do our instantaneous stretching, everything has gotten thinner, right? And if the crust gets thinner, that leads to subsidence. So we're going to have a syn rift subsidence due to the thinning of that crust. But now we have a little bit slightly more complicated problem, because what about the lithosphere? We haven't actually talked too much about the lithosphere. In fact, you never hear much about the mantle part of the lithosphere when you start doing isostasy, right? You all see the picture of the iceberg, and then you talk about the crust thinning and thickening and the root, and it gets higher, gets lower. But what about the mantle part of the lithosphere? This olive color lithospheric mantle, what's its density compared to the underlying asthenosphere? Well, we just went through the whole kind of density business. If it's cooler, it's more dense, right? So if there's no material contrast between the olive and the green, same material, the only thing different is the temperature. This is cool, this is hot. This one is more dense than the underlying underlying asthenosphere, right? Higher density, lower density. That's a little bit odd, because in fact this doesn't float. So in fact, this would be a problem if we didn't have the crust attached to it. This lithosphere could never float, right? It would actually just sink down into the mantle if we can get down in there. That's actually what subduction is, right? It's the oceanic lithosphere going back down because it's too heavy. Well, but for our local isostatic column, what's important about that is this is high density, low density. What happens if you take a lithospheric column like this and make it thinner? Rather than causing subsidence, that's going to cause uplift. Think about that for a moment, right? Here it's a thick, heavy column. Here it's a thinner, heavy column. It weighs less. it's going to float a little bit higher. So you have this immediate problem when you start stretching continental lithosphere, that you have a double effect. You're going to thin the crust, and that's going to make things go down, but you're going to thin the lithosphere, and that's going to make things go up. And you have to worry about both of those processes at the same time. That's actually built into this, but I'll let you discover that when you go to your homework assignment of this week. All right, so here's the quantification of exactly those processes. An initial geotherm is instantaneously stretched to this geotherm. That geotherm is then allowed to diffuse with time, giving each of these curves, and we can calculate then the temperature at every point in depth, and we can calculate what the thermal subsidence is. If you combine that then with the crustal part, then you'll get a full solution, which will give you a prediction then of the subsidence, that is the isostatic elevation, as a function of time. So here's going forward in time. This kind of a model then is going to predict that you get an instantaneous subsidence. That's due to the rifting. So this is all due to the crustal thinning, right? This is what we call then, this is then our model for the syn-rift subsidence. After that, it's going to start cooling, and that cooling is going to lead to more and more subsidence as we go down this one of these curves, by how much syn-rift extension we have. Right, so this is for a crustal thinning beta factor of 4. This is our syn-rift, and this is our post-rift subsidence, and following a thermal cooling curve. So this is what we see. This is the reason why we like these kinds of models, because if you go out to, say, a passive margin, or you go to look at a sedimentary basin somewhere in the continents, you see exactly this kind of a behavior. You have a total depth, say, of sediments as a function of time, and what you see is a kind of curve where it goes down, some kind of a curve that this is not a great example of that, but this is getting, it starts fast and it goes slower and slower with time. It always gets a little bit complicated because these sedimentary basins on land tend to be full of sediments. Sediments are heavy, so if you put relative to water or air anyway, and so if you put a sedimentary pile on top of the surface of the earth while it's cooling and subsiding, then in fact it goes further and faster than it would without those sediment loads. So you often talk about a total subsidence versus a tectonic subsidence. This is now just, again, this is depth, age. The tectonic model is saying we should be subsiding on a curve like this, but if you have a 1 kilometer hole in the ground, you fill it with sediments, in fact that pushes it down here. It can almost double that amount. So the total subsidence looks like it's about double of what that tectonic subsidence is. And the difference, again, is just the weight of the sediments. All right, so this is sort of our model for a stretching lithosphere. What else can complicate that? Well, there's lots of things that can complicate it. First of all, the syn-rift phase is not instantaneous. It can be slow. It could take millions of years, and so that's not going to give us a kind of instantaneous subsidence. The stretching doesn't have to be uniform. It can change with depth. There are issues with the type of strain, but I'll talk about that in a few minutes, so you'll hear more next week as well. And there are things like differences in asthenospheric temperature and other things that come into the isostatic calculations. So, and there are more listed here, but it's the same kind of ideas. There are lots of ways why this is not going to be simple, but in fact, it works pretty good. So here's another example. This one's actually maybe a little bit better than the first one I showed, but here's showing now in black a bunch of actual subsidence curves from sedimentary basin. Again, this is the West Siberian Basin. So these are from boreholes, but they're just showing how the age of the sediments changes as you go down the borehole. And what you see is that the fastest subsidence, fastest accumulation of sediments was relatively early, the first 50 million years or so here. And then they, actually this is only since the initiation of subsidence, so it's not even including the syn-rift part, but it's the fastest thermal cooling then is early, and then it's slowly becoming slower and slower. So if we looked at a Mackenzie type cooling model, that's what you get from like the blue or the red curves. Different initial lithosphere thicknesses, different crustal thicknesses, you get a different curve, and you can try and fit these and say something about what the cooling of the lithosphere is. The models on the right are showing some of these, the complications that come with this. For example, if you have a finite extension time or rate, then you can get the syn rift part can be much slower than instantaneous. You can get this sort of a syn rift phase that goes for millions of years or 100 million years, and then it starts to fade off into the thermal only later. This idea that stretching of the lithosphere is always uniform is almost certainly not true in general, right? We don't have a uniform stretch like this, but rather we might stretch more at the base and less as we go up, or you know, there's all kinds of different ways we can distribute that. But that's going to affect the isostatic response again, right? Rather than being just a box, we end up having to have some kind of an odd shape like this. Right, so for example, if it's kind of more of a necking pattern like this, we might have a different isostatic contribution from the crustal thinning. And here it's not uniform, but rather this kind of a funny shape, and the subcrustal lithosphere might be shaped something like this. So we'd have a more subsidence in the middle and less on the sides, which can lead to things like this sort of a pattern where you have a deep center to the basin, but you get this progressive onlap as the outer parts of the basin subside slower than the part in the middle. Simple shear, pure shear is an important question too. This is, again, how the deformation is distributed through the lithosphere. The simplest idea is actually the pure idea. If you have a pure shear, that means you have, if not uniform with depth, you have more or less uniform. We'll just call it uniform shortening with depth. Everything is shortening the same and it's fully symmetric. Simple shear means that you have some kind of a fault system. In this case, this is really a through lithosphere detachment. It comes all the way through the lithosphere like this, and the extension is taken up primarily on that one structure. So you could have the same extension. You can pull just as much on the ends here, but you'd put all of that displacement on one big fault. You'll have a lot of synthetic faults or antithetic faults all through the crust here, but most of it is taken up on this detachment, or what we often see is some kind of a mix of this, where you might have a simple shear in the upper crust like this, and then pure shear in the lower crust in the mantle, where the higher temperatures mean that the rheology is somewhat different. And of course, this is going to change a lot the pattern of subsidence that you have, and the subsequent thermal subsidence, as well as all the structures, of course, you see up in the near surface, right? So this, for example, is almost a symmetric graben type structure, whereas here it's going to be highly asymmetric, here even more so. Here's sort of an example of some of the things that are predicted from these kinds of simple shear models. So here again is this through-going ductile shear zone all the way through the lithosphere. First of all, what it's going to bring up the lithosphere in this region, then, sorry, the asthenosphere under the lithosphere in this region, right? The lithosphere is being thinned here, right? Whereas the crust is being thinned way over here because of this dip on this ductile shear zone. So here we might have, again, this, we'll slowly pull up this detachment zone. There will be all of these extensional structures along here and the crustal deformation along here. But in fact, as the asthenosphere rises up underneath the crust here, this can cause uplift of this area. Again, because we're replacing high density mantle with low density mantle, this is going to lead to uplift. So the uplift subsidence pattern might be asymmetric and show a pattern something like this. Thinning of the crust here, thinning of the lithosphere here. Right, so there's a number of predictions. Well, this is just sort of to put them on a list for you, but you can kind of go through the different, some of these different predictions if you'd like. All of it comes down to what are the strain distributions through the lithosphere during this kind of a stretching event. Uniform, non-uniform, asymmetric, pure shear, simple shear. What are the structures? What's the distribution of crustal thinning and lithospheric thinning? Another example of a different style of rift. So again, back to our key model here now. If we look at what's relatively slow and distributed strain, there are what we recognize as extensional tectonic domains or regimes that really don't look anything like rifts. So everyone always has a picture of a rift valley in their head when they talk about extension, but they don't have to look like that. This is an example on the bottom here of the western United States. So this is California out here. Maybe some, no, I don't even see, these are county lines. You guys won't know that, but this is going across the western US from California through Nevada, Utah, and this region. These are all little mountain ranges, all these lines, and this is in fact what we call the basin and range domain, where each of these is in fact a little extensional structure. These are all little tilt blocks on normal faults, and they're the topographic expression is from the tilting of the footwall of these normal faults. So this is a region now that is hundreds of kilometers across. So here's, oh, here we got, now we have the state boundaries, so I can find myself anyway. California, Nevada, Utah. This is the Rocky Mountains are out here, but this entire region in here is under extension. Most of that extension is focused on the edges of the domain, but the entire region has been stretched and extended. And this is a small, slow strain, but slow strain rate, but it's still strain over this entire region. So this is kind of this wide versus narrow rifting. There's different ways it's been suggested that you can get this from, you know, depending a lot on the rheology, and I think Whitney will talk a lot more about that next week, but we can go from this very simple graben structure. Here's just two normal faults and a graben with shoulders on the side. We can begin to widen that out symmetrically. We can turn that into an ocean basin if we cut that off and put all of that strain here. We'll leave behind then half of the normal faults here, the other half are somewhere over there. Wide rifts don't even necessarily have to be rifts. It's been argued, in fact, that this is what we see often in old mountain belts. We have very thick crust, and it can be that, in fact, this thickened crust actually undergoes extension just from gravitational forces. So rather than trying to stretch and create a new ocean basin, it could be that we just have a big old orogenic belt, very big, not kind of alpine size, but more like Tibetan size. And when that compression stops, then we go into some kind of an uplift and extensional phase with all these normal faults being distributed across the upper part. Right, okay, well, I think that's good for today. I'll have the slides posted up for you, and there'll be a homework distributed in the next day or so as well. So thanks for your attention.